Dear students, in this class, now let us discuss about the order properties of real numbers. Actually, what is a real number and some of its properties. So here let us discuss about the order property. What is an order property of set of reals? So you can first consider a set of positive real numbers. Suppose letter P be the set of positive real numbers. Consider the set P be the set of positive real numbers, is positive reals having some of the properties. Means first one is P is closed under addition. Second one is P is closed under multiplication. P is closed under addition means if we choose A comma B, for only A comma B following P, means when A and P are positive real numbers, then A plus B also following P. Here we say that P is closed under addition. For all A comma B following P, then A into B also following P. So P is closed under multiplication. So consider set as P is construct a set P, the set of positive reals having the properties P is closed under addition, P is closed under multiplication, and also if for only A fall in B, if any A fall in P, A fall in R, if any A is a real number, if any A fall in R, then exactly one of the following hold here. Either A fall in P or A equals 0 or minus A fall in P. This property is known as the trichotomy property. This property is known as trichotomy property. So you can construct a set of real numbers P having the properties P is closed under addition, P is closed under multiplication, and the trichotomy property. That is, for any real number A, either this A is positive real or A is 0 or minus A is a positive real. Come on. So construct such a P. Then if A fall in P, what happens? If A fall in P means A is in P, A is a positive real number, means A should be greater than 0. If A fall in P union singletons to 0, P is, what is P? P is set of all positive reals only. 0 does not include it. If you consider this set, P union singletons to 0, then this is a set of all positive reals including 0 itself. So if A fall in P union singletons to 0, then A is a non-negative real number. Here A is a positive real number, here A is a non-negative real number, A greater than or equals 0. Similarly, if minus A fall in P, minus A fall in P means, what is A? Minus A fall in P, P be the set of positive real numbers. So minus A is a positive real number. That happens only when A is a negative real number, means A should be negative. Similarly, if this minus A fall in P union singletons to 0, then clearly this A less than or equals 0 means A is a non-positive real number. So consider this P. P is constructed in such a way that P is closed under addition, closed under multiplication, and having the trichotomy property. Okay. So now consider the result. The result is so immediate, and it is so obvious. If A, B, C are any three real numbers, A, B, C are any three real numbers, then if A greater than P, if A, B, C are any three elements, then if any three real numbers, if A greater than B and B greater than C, then this should implies A greater than C. If A greater than B, B greater than C, then A greater than C. So we know that this is it's a familiar result. So we know this result. But how to prove this one? A greater than B means how to prove? A greater than B. A greater than B means that should implies A minus B should be positive. A and B are real numbers. So A minus B is also a real number. Why? Because set of real numbers is closed with respect to this subtraction. So when A greater than B, surely this A minus B is positive. We know that A minus B is positive means this A minus B should be fallen by P. Why? Because P is constructed in such a way that P is the set of all positive real numbers. So A minus B fall in P. Similarly, B greater than C. B greater than C. That should imply B minus C is also positive. Okay. B minus C is positive means this B minus C also fall in where? But we know means A minus B is an element of P. B minus C is also another element of P. We know that P is closed under addition. So we have A minus B plus B minus C also fall in where? P itself. A minus B plus B minus C also fall in P. Why? Because P is closed under addition. That means this means A minus C fall in P. A minus C fall in P means A minus C is a positive real number. That is A minus C should greater than 0. A minus C greater than 0 means A greater than C. So this is what we require here. So when A greater than B, B greater than C, then surely A greater than C. Okay. Means this is a transitive property. So the transitivity of this real numbers is proved as in this way. Okay. Now, if A greater than B, consider another result. If A greater than B and then A plus C, then A plus C greater than B plus C. If A greater than B, then A plus C greater than B plus C. How? That's again immediate. We know that that's a trivial result. But how to prove this one? A greater than B means A minus B should be positive. Why? Because A greater than B. A minus B means, yes, it is A minus B positive. A minus B positive means A minus B should be falling the P. Why? Because P is the set of all positive rates. A minus B fall in P. Then since C being a real, what is C? C is any real number. C is a real number, and when A minus C or yes, it is A greater than B, A fall in P, A minus B also fall in where? P itself. Now, clearly, if C fall in P, C is a positive real. What happens here? If C fall in P, and or if C means if C is positive, or C fall in P, or if C greater than 0. There are two possibilities. A is greater than B, then A plus C greater than B plus C is our requirement. A minus B, since A greater than B, A minus B fall in P itself. If C is positive, then A minus B into C also fall in P. Why? Because P is closed under multiplication. Agree. That means by the distributive law, it is AC minus BC fall in P. Yes, so it is A minus B or AC minus BC. Sorry, it is not our product. Sorry. A minus B is positive. Our requirement is A plus C greater than B plus C. Sorry. A plus C greater than B plus C. A minus B is positive. Then surely A minus B fall in P. And consider it is A plus C minus of B plus C minus B plus C. Consider this A plus C minus B plus C. A plus C minus B plus C means it is A minus B. Minus and plus C cancelling each other, but A minus B. But we know that A minus B fall in P. Okay. That means you can conclude that this A plus C minus of B plus C should be falling where? Should be falling B. That means this A plus C greater than B plus C. So this is the requirement. Okay. When A greater than B, for any real number C, then this A plus C greater than B plus C. Okay. Now we know that another result. If A greater than B, then AC greater than BC or CA greater than CB. If A greater than B, then AC greater than BC. How to approach this one? If A greater than B and C is positive, where C greater than C. If A greater than B and C greater than C. A greater than B means A minus B is positive. So A minus B is positive and C is positive. That means A minus B fall in P and C fall in P. Okay. A minus B and C are the elements in P, but P is closed under multiplication. That means A minus B into C also fall in P. So by distributive law, it is AC minus BC fall in P. Why? Because it is closed under multiplication. So AC minus BC fall in P means, or A minus B into C fall in P means, clearly this A minus B into C should be positive. Okay. So that means it is AC greater than BC. Agree? If A greater than B and C is negative, what happens here? The next is, if A greater than B and C is negative, what happens here? Then CA or AC or CA less than CB or AC less than BC. The proof is same as in this way. Why? Because A is A greater than B, A minus B is in P. Okay. This can be proved as in this way, means A minus B greater than 0, that means A minus B fall in P. C is negative. C is negative means minus C should be a positive real number, so minus C fall in P. Since P is closed under multiplication, so it is A minus B into minus C fall in P. So that means minus AC plus BC also fall in P. Or which is a positive real number, that means minus AC plus BC greater than 0. So it is AC less than BC. Okay. So this is our requirement. So by using the order property of set of real numbers, we can prove our trivial results in this way. So these are some interesting cases. Okay, we can prove our trivial results by using the order properties of set of reals. Clear? For that, we can construct set of real numbers, or P, construct a new set of P which has the set of all positive real numbers having the property which is closed under addition, closed under multiplication, and having trichotomy property. Okay. Now listen. Now let us go to another research. That is, if A is in R, if A is a real number and A differs from 0, then A square is positive. If A is any real number, we know that's familiar, that's trivial. If A is a real number, A is non-zero, surely the square of a quantity that should be positive. Okay. What is set of natural numbers? By using this argument, we can show that set of natural numbers is positive. So listen here. A is real. If A is R, A differs from 0. A differs from 0, then either this A is positive or this A is negative. Okay, it's a positive real number or a negative real. If A is positive, what happens here? A positive means we know that A is a positive real number, A is foreign P. Okay. Since A is foreign P, P is closed under multiplication, so A into A also foreign P. Sure. Why? Because P is closed under multiplication. So it means A square also foreign P. A square foreign P means what is A square? A square is positive. Finished. So when A is positive, A square is positive. Case again, since A is non-zero and if A is negative real number, A is negative means what is minus A? Minus A is a positive real number. So minus A following P. Since P is closed under multiplication, so it is minus A into minus A also following P. Minus A into minus A following P means it is A square following P. So that means A square is also positive. Agree? So when A is any real number, if it is non-zero, then A square should be positive. So the result is so familiar, but it can be proved by using these arguments. Okay. How can you prove this 1 is positive, 1 greater than 0? Put A equals 1. 1 is a real number. Then since 1 is not 0, 1 is positive. So it is 1 greater than. Then 1 into 1 is positive, 1 greater than 0. Okay. Suppose, consider n. N is a natural number. How to prove this n greater than 0? We know that. Set of natural numbers. What is set of natural numbers? N equals set of 1, 2, 3, 4, etc. Okay. So we know that all of these natural numbers are positive. That's familiar with us. But how to prove that one? N greater than 0. N is any natural number. N greater than 0. Listen. Put n equals 1. We know that when if you replace A by 1 here, 1 is positive. So 1 greater than 0. So it is true for n equals 1. Okay. Now suppose this result is true for n equals k. For any k following n, then this k is positive. Why? Because the result is true for n equals k, means k is positive. K is positive means this k should be following by p, our set to be. Okay? Yes. Then we know that here what is 1 greater than 0, so here 1 following p. Then clearly 1 following p and k following p, 1 and k are two positive reals that presents in p. Since p is closed under addition, surely k plus 1 following. Okay. Means the result is true for n equals k plus 1. Then n equals 1, the result holds. And we assume the result is true for n equals k. Now we prove that the result is true for n equals k plus 1. So by induction hypothesis, this result is true for every natural number n, therefore n following p. That means n greater than 0. Okay. So by using the order property, we prove that set of natural numbers or each natural number is a positive real number. Agree? Thank you.